Hello, this video is about the formal verification of a model in TTool. At first, we're going to open a model, File, Open Project from TTool repository, and we select Coffee Machine. Save. The requirement view opens, but our interest in this video is about the design of this coffee machine. The main diagram of this coffee machine shows four main blocks: coffee machine, coffee button, tea button, and a wallet. Let's first open the behavior of the coffee machine. In the coffee machine, there is a state machine which waits for a first coin. When this coin is inserted, I'm going to zoom, get coin X. This number of coins is increased by X. X will be equal to 1 in this design. Then the machine waits for a second coin. If this coin is not inserted before a given delay, the system, after coin delay, goes to eject state and sends the message eject coin, number of coins, which is, if X is equal to 1, to 1. The number of coins is equal to 0 now, and the machine goes back to this state. Then, if there was a coin which was inserted before the expiration of this delay, the number of coins is now 2, and the system goes to this composite state, which is called beverage. Let's zoom more. Beverage. This composite state starts here, waiting for selection. There can be 3 different actions: push coffee button, push tea button, or eject coin after a given delay. So if there is no selection of a beverage before coin delay, the machine ejects again all the coins which were inserted, and the number of coins is equal to 0. If push coffee button is pressed, then after a given delay, coffee min delay, coffee max delay, the coffee is delivered and the system goes back to waiting for first coin. Of course, number of coins is set to 0. Same for tea button, but with tea min delay, tea max delay. Let's now see the behavior of the coffee button and tea button. Let's start with the tea button. Very simple. Main, there is a push. After a mechanical delay, there is a main. It goes back to main. Coffee button. Just to show you how to use composite states again. Main, state 0, start here, push. After a mechanical delay, main. So the buttons don't have a very complex behavior apart from this mechanical delay. There is still one last block of importance in this model, which is the wallet. The wallet starts by executing a method which is only there for documentation, and the system goes in the main state. There are 2 possibilities from this state. Either the wallet receives coins from the machine, if there was an eject coin, so the wallet gets coins and increases its internal number of coins by X. Or the wallet decides to insert one of its coins in the machine. It's with the put coin action. After a user delay to get the coin and insert it, the number of coins in the wallet is decreased by the number of coins which were inserted in the machine. And the system goes back to main. Again, there are different methods which are used there for documentation or code generation. This is not the purpose of this video, so their use is not presented here. But you can totally ignore this in the scope of formal verification. Okay, now you know how the system works basically. Now we're going to verify it. Let's go back to the coffee machine. In coffee machine, maybe you have noticed that there is this RL question mark on 4 actions: get coin, push coffee button, push tea buttons, eject coin. This is a way to tell the system I would like to study the reachability and liveness of these actions. Reachability means that we would like to know if there is at least one path, one execution path leading to this action. Liveness means that we would like to know if in all possible paths the system executes at least one time this action. So we're going to verify this. For this, we first need to check the syntax of the system. Blocks taken into account are all the blocks which were captured. Syntax check. No warning, everything's fine. If there were to be errors, they would be listed here. But there are no errors. Same for warnings. Okay. Now we click here. Safety verification. A window should open. And we're going to say that we would like to study the reachability for the selected states and same for the liveness. And we can click on start. It should be quite fast. And we can go back to the model. And now we see that actions we have selected before have been annotated. It's possible to put the second coin in the machine, but there are execution trace in which the second coin is never put in the machine. Same for coffee button, tea button, and eject coin. Actually, eject coin is not reachable. The three others are reachable. Actually, a coin is never ejected because always in this system, a tea button or coffee button is pushed before the coin is ejected. Okay, why is the liveness not satisfied in this system? Well, simply because of this. In this system, it's always possible to eject the coin. It's possible to insert a coin, but it's also possible for the machine to eject the coin. So there is an infinite loop in which the coin that is first inserted is always ejected. So the system, in that case, will never deliver a beverage. Okay, let's now analyze the reachability and liveness of all states of the state machines. To do this, I need again to check the syntax. And now in the verification window, I will check all states there. And I click on Start. And now all the states of the model are annotated. And we see that here the reachability is satisfied until this point. Because it's always possible to always get a beverage or to always eject the coin. So the two branches are the liveness, which is not satisfied. If we go in other state machines, we see that for T button, main is always reachable, and this one probably as well. Same here, and the liveness is satisfied. And for wallet, main, the liveness is satisfied, reachability is satisfied. This is the same state here. And get coin, and the liveness which is not satisfied, and reachability is satisfied. Which means that it's possible to only put coin in the machine, and so coins will never be ejected. Okay, when we want to go further in the behavior of the system, we would like to investigate all possible execution traces. To do this, we're going to generate a graph which shows all these possibilities. It's called a reachability graph. To do this, we need again to check the syntax, to click again on the same icon, but this time we're going to check reachability graph generation. Start. Okay. And now a reachability graph has been generated. It is accessible here. What I'm going to do is do show. This graph shows all the possible execution paths starting from the grids green state, which is init state, until the red states, which correspond to a termination or a deadlock of the system. So if we try to figure out what happens, you could zoom. We've got a way to do this, so there is a loop there, okay, or like this, which corresponds to inserting a coin, ejecting a coin. Then if a second coin is inserted, there is a push coffee button or a push tea button, and the system terminates because there are only 2 coins in my wallet at first. Here. So once the 2 coins have been used, it's not possible to get another beverage or to insert another coin. So the system terminates. Of course, you could try to modify this number of coins and see that the graph is different. If you put only 1 coin, it's not possible to get a beverage. If you put 3 coins, it's possible to get a beverage and insert 1 more coin, but not possible to get a second beverage. If you were to put number of coins is equal to 4 at the beginning, you could get 2 beverages. Okay, but you see that this graph is not so readable. Even if external actions, so exchanging signals, is put in green, and internal actions of blocks are put in black, are written in black. Sometimes the graph is really not readable, it is too big. In that case, there is only one way if you want to verify the system, to understand the system for sub-actions of this graph. You can minimize the graph. For this, you go there, you right-click, minimize. And then you can select the action you want to take into account in this generated graph. So I'm ignoring most actions. I'm going to take into actions only, let's say, push and eject. Now I'm going to minimize a graph which will contain only these actions. Now I've got a graph with 2 states and 3 transitions. It's here I'm going to show this graph. Obviously, it is much easier to analyze this graph. From state 0, there is a loop on eject coin, and at some point, coffee button or tea button actions can be executed and the system go to termination. So we can easily see that it's possible to do this indefinitely, so these actions are reachable, but their liveness is not satisfied. This is another way to prove it. Obviously, sometimes you would like to express more complex properties than simply reachability of liveness of a state or of an action. To do this, you've got a block which is called safety pragmas, which can be added to this diagram. To do this, you can click here and then click on the panel. Okay, how does it work? You can double-click on the box and you obtain the list of pragmas I have entered before. And if you click there on the question mark, you obtain the help on properties. There are 4 properties. I'm going to explain them progressively. First, to express a property, you can start with a letter, which can be A or E. A means on all paths, and E means on one path. Indeed, the safety pragmas express properties according to the reachability graphs. But in TTool, you don't need to generate the reachability graph to study these properties, but I'm going to explain how to check these properties later. A, and then there is an operator. Square brackets or less than, greater than. Square brackets mean on all states, all path, all states. Here it means one state. All path, one state. all path, all state P should be satisfied in all states in all paths, so everywhere in the graph. The second property, again, it means one state of all paths. There is a path here, P is satisfied. There is a path here, P is satisfied. There is a path here, P is satisfied. So E means one path. Square brackets mean all states. So we need at least one path in which P is satisfied in all states. This is not true for this path, but this is true for this path. P is satisfied in all states of this path. Last property with starting with a letter, E less than greater than a property P. It means in one path, one state. It means reachable. One path, one state. And there is a last properties which is named leads to. So these two properties are written P arrow Q. It means whenever P is satisfied in a path, it must be followed by Q in all paths starting from P. So P is satisfied here, right? It is followed by Q in this path, and it is followed by Q in this path. The property is satisfied. Now I'm going to explain you how to express P properties. Let's take examples. Closing this, coming back to safety pragmas, I'm going to take this pragma first. A square brackets means that we would like the property P to be satisfied in all paths, all states. Coffee machine number of coins is less or than or equal to 2. We know that coins at first, number of coins is equal to 2 when starting. And we know that we can inject, receive what we injected before, or select a beverage, and then have no more coins in the wall. So we know that this is true in all state, all path of the graph. But we're going to verify this afterwards. Let's take another property. This one. Coffee machine beverage leads to coffee machine coffee delivered and coffee machine tea delivered. And we know that once we've been in beverage, we can select only one of the two, not the two. So this will be not satisfied. If we put an OR between those two states, now it will be satisfied. It means that after beverage, after reaching beverage, there will be a coffee delivered or a tea delivered. Sometimes the fact that a safety pragma is not satisfied is fine. That is, you expect a pragma to evaluate to false. You can specify whether you expect the pragma to be evaluated to true or false. For instance, this pragma, you think it is true. So you put a true before. And you put a F when you think a pragma is not satisfied, that is, it evaluates to false. When you put nothing, it means true before. But let's evaluate these pragmas. Syntax checking. Window for selecting pragmas. So here I'm selecting all pragmas. And I'm clicking on Start. And now I've got the result. When there is a green check, it means that the pragma is satisfied. When there is a red cross, it means that the pragma is not satisfied. All of them are satisfied until the red cross. We expected this one to be indeed false. Since there is nothing before, it means true, and we know that it evaluates to false, so there is a red cross. Okay, sometimes we would like to know also why a pragma is satisfied or why it is not satisfied, why there is a red cross. So let's go again in syntax checking. Dialog window. checking, and now I'm checking generate property AUT graph trace. So it's going to generate either a graph or a trace to show why the property is satisfied or why it is not satisfied. We can do this only for a subset of properties, so do not be surprised if you write a safety program and the system does not generate a trace. Okay, start. Okay, and now I've got a collection of traces there in the tree on the left. So for instance, for this property, coffee machine number of coins is more than 0. There is a path with at least one state in which this is true. This is true. And it managed to compute a path, and we can make show on a trace to show it. So at first there is a put coin, and that's it. Let's take one in which it is false. So there is this one, okay, which is, and its corresponding trace is here.